Hello, and welcome to my channel called Statistics from A to Z, Confusing Concepts Clarified. These videos are based on content from my book of the same name, which is published by Wiley. For more information on the book and these videos, please visit statisticsfromatoz.com. This is the fourth of 6 videos in a playlist on ANOVA and related concepts. There are 4 videos on ANOVA only. This part 4 video is about the 2 different types of two-way, also known as two-factor ANOVA. Depending on when you are viewing this, videos 5 and 6 may not be available yet. To get the latest status, see the videos page on the book's website. As usual in the book and in these videos, we'll go quickly through a list of keys to understanding, or KTUs, and then we'll go into detailed explanations of each of the keys. The first key to understanding is, in two-way ANOVA, we study the effect of 2 nominal, that is named, variables, A and B, on the dependent numerical variable y. A and B are factors influencing the value of y. AB, the interaction between A and B, can be the third factor. The second KTU says that there are 2 methods for two-way ANOVA. The without replication method can be used if there is no interaction which is statistically significant. Otherwise, you must use the with replication method. Key to understanding number 3 says, two-way ANOVA with replication simply repeats, that is replicates, the experiment several times for each combination of A and B values in order to obtain sufficient data to identify and quantify any interaction AB. And the final KTU, number 4, tells us, in an ANOVA table, P less than or equal to alpha indicates statistical significance. If, in the with replication method, the interaction AB is statistically significant, then p-values for A and B are not usable. And here on one page, we summarize everything you need to know about two-way ANOVA. You may wish to pause the video now and read all of these keys together. Let's now begin our detailed explanation of each key to understanding. The first part of KTU number 1 says, in two-way ANOVA, we study the effect of 2 nominal, that is named, variables, A and B, on the dependent numerical variable y. Now we are all familiar with functions such as y equals f of x or y equals f of x1, x2, ... xn. In two-way ANOVA, the equation is of the form y equals f of a, b, ab. Y is the dependent variable. Its value is a number. In our example, y is a numerical measure of cleanliness. The values, which are the variables a and b, can take on names, not numbers. They are nominal named variables. For example, let's say we want to compare the cleaning effectiveness of 2 brands of detergent in 3 temperatures of water. The y variable cleanliness is a numerical measure of whiteness of the cloths that have been laundered. In our example, y can take on numerical values between 0 and 50. A and B are nominal variables whose values are names. A can only take on one of 2 values, the names detergent number 1 or detergent number 2. We will test 3 temperatures of water for variable B, cold, warm, and hot. Note that while water temperature can be measured by the number of degrees Celsius or Fahrenheit, we are using names, not numbers, and there are only 3 values for water temperature. Y is a function of A, B, and AB. Y is the dependent variable in the function y equals f of A, B, and AB. It is also known as the outcome variable. A, B, and possibly AB are the factors influencing the value of the outcome variable y. We don't call them independent variables because the interaction AB is not independent of A and B. Before doing a test, we don't know if there is an interaction between the two factors. The two-way ANOVA test will tell us whether there is a statistically significant interaction between A and B. The table summarizes what we've learned so far using this example. We have the dependent or outcome variable y, which can take on the numerical values of 0 through 50 in our example test. We have three factors, A, B, and the interaction between the two, AB. Factor A is the type of detergent, taking on the two named values, detergent number 1 and detergent number 2. Factor B is the water temperature, taking on the three named values, cold, medium, or hot. In the interaction factor, which may or may not exist, it involves combinations of A and B. In one-way ANOVA, we worked with samples of data in a population. In two-way ANOVA, we design experiments to ensure that we get the kind of data that can be analyzed the way we need. KTU number 2 tells us that there are two methods that can be used for two-way ANOVA. The with replication method is usually better because it uses more data and provides more information. However, if the experimental budget or time are constraints, the without replication method can be used, but only if there is no interaction between the two factors. But how do we know whether there is or is not an interaction? The answer is plot the data. If the lines don't intersect, there is not a statistically significant interaction. We need to perform experiments which measure the y variable for each combination of factors A and B. In this example, we have 3 values for factor B and 2 for factor A, so there are 3 times 2 equals 6 combinations of A and B. They produce 6 values for the y variable. In the left example diagram, we see the case in which detergent number 1 has a stronger effect than detergent number 2, no matter the water temperature. Detergent has an effect, water temperature does not. The middle diagram illustrates the case in which both factors have an effect, but both detergents are affected the same by changes in water temperature. However, in the right diagram, we see that the two detergents are affected differently by changes in water temperature. Hotter water makes detergent number 1 perform better, but it makes detergent number 2 perform worse. The lines cross, so we have an interaction between the factors A and B. If the graph shows no interaction, we can use two-way, also known as two-factor ANOVA, without replication. Our experiments need to measure y variable data only one time for each combination of A and B data. Factor A has I number of values to test, and factor B has J values to test. If that's the case, then there are I times J pairs of combinations to test. In our example, there are 2 detergents for factor A and 3 water temperatures for factor B. So there are 2 times 3, that's 6 combinations to test. As shown in the table, each of these 6 tests gives us a numerical value for the outcome variable y, which is a measure of cleanliness. Each statistical spreadsheet or software tool will have a somewhat different format, but here is an example of the type of information provided by the without replication analysis. In this example, the source of variation column calls factor A rows, and it calls factor B columns. To determine if there is a statistically significant effect for either factor A or factor B, we can look at the p-value. In both cases, the p-value is well below the value of 0.05, which had been selected for alpha. So both factors A and B have a statistically significant effect on cleanliness. The columns SS, DF, MS, and F provide some background information, which is explained in the Part 3 video. The without replication method has lower experimental costs, but it is limited. It does not identify or quantify interactions. KTU number 3 says, two-way ANOVA with replication simply repeats, that is replicates, the experiment several times for each combination of A and B values. This is in order to obtain sufficient data to identify and quantify any interaction AB. Suppose we perform tests which produce this graph. The lines are somewhat separated, but are they separated enough for us to say that factor A detergent has a statistically significant effect? The lines are slanted, indicating that factor B, water temperature, has an effect, but is it a statistically significant effect? Now, the two lines don't cross, but if extended, they would. Does this indicate a statistically significant interaction? Given this uncertainty, it may be unwise to try two-way ANOVA without replication. The graph is ambiguous enough that we may want the greater accuracy which is achieved by using more data points, as with the with replication method. That would also answer the question of whether or not there is an interaction. The with replication method repeats, that is, replicates the experiment several times for each combination of A and B value. This table shows 3 measurements of Y have been collected for each combination of A and B data. That can provide sufficient data to identify and quantify an interaction. The number of replications required to achieve a specific level of accuracy is determined by the methods of design of experiments, or DOE. The book has a 3-part series of articles on DOE. Here's the ANOVA table, which is calculated from the with replication data on the previous slide. The first thing we need to do is to check the p-value for the interaction AB. It is 0.660. Alpha, as shown in the top row, was selected to be 0.05. If the p-value indicates a statistically significant interaction, then this happens when p is less than or equal to alpha, then the p-values calculated for A and B separately would be meaningless. The effects of A and B would be too intertwined to separate them. In this example, the p-value at 0.660 is greater than alpha at 0.05, so we do not reject the null hypothesis. The null hypothesis of no statistically significant effect for the interaction is supported by the ANOVA analysis. Note that there are 3 different null hypotheses here. There is one each for factor A, factor B, and the interaction. Since there is no statistically significant interaction, we can check the p-values for the 2 factors, A and B. If p is less than or equal to alpha, then that factor does have a statistically significant effect. The null hypothesis of no statistically significant for the factor is rejected. In this example, the p-values for both factors A and B are less than alpha, so we reject the null hypotheses for them and conclude that both factors A and B do have statistically significant effects on the outcome variable Y. Okay, that's it for our clarification of this confusing concept. If you like this video, please remember to press the thumbs up like button on your screen below. I'll be making more videos of some or most of the 60+ concepts in the book if folks like you tell me that more videos are wanted. Please subscribe to this channel to be notified when new videos are uploaded. Also, the website statisticsfromatozz.com has a listing of available and planned videos. Now, videos like this one can be very helpful, but they're not very handy when you want to quickly look up something on the job while studying or during an open book exam. For that, nothing beats a book or an e-book. You can also learn more about those on the website. I'd recommend following my blog at statisticsfromatoz.com/blog. I've got some things there that hopefully you will find interesting, like a Statistics Tip of the Week series, as well as posts showing that you are not alone if you're confused by statistics. I'll also be posting on the Facebook page, Statistics from A to Z, and on Twitter as @StatsA to Z.